welcome to the next episode of Klingberg Wing Mark II Development. I'm Raul Klingberg, your host. Today I want to talk about some trade studies I've been going through in preparation of making new D-tubes for the new wingtip panels. It seems that recent flight tests and surrounding tests of fixes are showing that I'm going to have to build new wingtip panels for the wing. Not going to be able to get the level of controllability that I want with the current wingtip panel. It's going to have to extend the elevons. At least I hope that solves the problem. But in preparation for that, I've been cutting parts and getting ready to build new wingtip panels. And as a part of that process, I thought I'd take it as an opportunity to improve the design. Now, overall, the design of the wingtip panels is very good. They have the sufficient strength to weight ratio, and they've proved to have really pretty darn good durability. I think they could be made a little bit lighter, and on the durability side, the D-tubes themselves are kind of prone to getting dented. The fiberglass over the foam is not as durable as I would like to see, and I think it makes it a little too high of a maintenance issue. So if I can make them a little bit durable, a little bit more lighter, that'd be good. So I've recently done a series of trade studies with the foam core material and different skin materials, different cloths, to see if I can achieve that goal. And things have worked out in quite an interesting way. Where I ended up was a little different than I expected, and I'd like to share that with you, so maybe you can incorporate either some of the ideas directly or just the basic process of how to come to these conclusions into your own designs. So that said, let's get ready to sit down and talk about trade studies for making D-tubes. Okay, so we're back, we're ready to go here, and we're going to have not as long as last time, it won't run an hour, but we'll have a fairly detailed discussion of the trade studies that I went through to find a way to build these D-tubes both lighter and more durable. And I have managed to achieve both. Now I haven't actually made the D-tubes yet, so the proof's in the pudding, but I have a way to do it. And I thought I'd show you how I ended up getting to those conclusions. So you see in front of me here 3 different rolls of cloth that I use for the trade studies. Here I have some 120 satin weave fiberglass, pretty standard stuff, runs about $8-9 a yard, something like that. I have some 2-ounce basket weave fiberglass cloth. These are both E-cloth. And what does this stuff run? I think I paid about the same amount of money for that. Here I have some 120 Kevlar. This is 1.8 ounces per square yard, and it's a pretty standard Kevlar that's used in a lot of lightweight aircraft. It is fairly spendy. I got this at a pretty good deal on this at about $28 a yard, but I've seen it as high as $40 and up in some places. Kevlar's gotten very expensive. It now runs the same as, if not more than, carbon fiber. And I'll be discussing shortly why I chose this over carbon fiber. But first, let's talk about the original construction of the D-tube. So this D-tube was made of 1/16 inch thick Aerex foam core material. It's a PVC-based foam made over in Europe. The outside is 3-ounce fiberglass cloth. It's this 120 satin weave on the outside, and on the inside is the spread toe carbon fiber cloth. It's a relatively new material. A lot of folks have been using it. It's very expensive. This spread toe stuff runs anywhere from $70 to $90 a yard. So we see quite a spectrum of costs here. Now, if you've watched my other videos, you know why this is designed the way that it is. I'm carrying all of the loads on the interior skin. Well, let me put it this way. This is designed such that the loads carried by the internal skin are sufficient strength for all of the flight regime. In other words, it doesn't need the outside skin to carry loads. The outside skin does carry loads, but it's not needed, it's not included in my calculations. So I designed this such that the inside skin is sufficient, gives the wing sufficient strength. And then the idea with the outside skin was to protect the foam, provide an aerodynamic surface, but not necessarily to carry loads. Now, of course, loads are transferred through the foam via shear. How much is transferred, I don't know. I've never made an attempt to calculate it or measure it because it just wasn't important to me. But I consider the outside skin to be margin on the design. Just a little extra load carrying capability. Now, it's came in not too bad. This weighs 2.5 ounces per square foot, so this whole thing weighs a little more than a pound. This is the full D-tube for the leading edge of the tip panel, and overall it's worked out quite well. The wingtip panels have proved to be very durable. Flopped down on the ground a couple of times after stalls, and I actually ground looped it once, and the wingtip panels have held up just fine, with one exception. They've been a little bit tender in terms of durability. They dent easy. And I knew this was a potential problem when I made them, and I made various design decisions based on a multitude of factors that ended up at this design. And for a one-off, a first aircraft one-off, it's fine. There's nothing wrong with the design that prevents it from working. However, if you wanted to have this aircraft long-term and do hundreds of flights on it, it probably needs some upgrading to meet all of those requirements. Now, the requirements I laid on this were, had to have the sufficient strength-to-weight ratio, had to be materials that were readily available, had to be cost-effective, and it had to be buildable using methods that a home builder could easily handle, your average home builder. If this aircraft were designed to be delivered ready to fly or as a kit, I would do it differently. The design would come out different. So part of the reason that it is the way that it is because it's for home builders. And in the process of meeting that requirement, there's certain compromises I had to make. Now, one of them was cost. Yeah, it's not structure, it's not aerodynamics, but there are many factors that have to be considered, and cost is certainly one of them. And when you're laying down cloth that's $8 or $10 a square yard, as opposed to, say, 40 or 75 or 90, it makes a difference. It can come into the hundreds or even thousands of dollars in materials for building the aircraft. And one of the holdbacks, I think, on this type of glider for the general hang glider pilot is cost. How many people have $40, $50, $60,000 for a Swift, or $100,000 or $110,000 for an Aerotrix? It's just untenable, and then you have to wait 2 years to get one. And heaven forbid you crash it, you break a wing panel, you got to buy a whole new wing panel. A very expensive proposition. So, by being home buildable, I wanted to try to provide to the flying community an aircraft design that they can make cost effectively, and if they do break something, they can repair it. And fiberglass goes a long ways to meeting those goals. It's not the lightest weight solution, and it's not the most durable. When I did my test samples of wing skin, I went through a lot of variations looking mostly at strength-to-weight ratio, and a lot of it was driven by weight. And I was looking for so many ounces per square foot so that I could build the wing to meet my 100-pound weight goal. And on an aircraft like this, these wing skins, anywhere that's covered with a composite sandwich panel, that's the weight driver. All of the weight is in the skin. And the pilot's cage, yeah, that adds some, and control system, that. But the main driver, wing skins. So if you can get the weight of the skins down, you can save a lot of weight on the aircraft. In fact, on my design, started out with the whole thing being like the Swift. It was all going to be skinned with composite material, but it was simply too heavy, 150 pounds, 160 pounds. So I went with composite D-tubes, fabric and ribs for the aft portion behind the spar, and at the root area, it's skin everywhere to take the torsional loads that are imparted there. So that was another compromise in order to meet the strength-to-weight ratio. So in the process of making all those samples, I would play with them and make sure, check their flexibility and their durability. And part of the durability process is I would go and try to dent them. And I noticed that carbon fiber is bad to have on the outside. Fairly easy to dent because it's only one thin layer of like 3 or 4 ounce cloth. And not only that, when it dented, it tended to crack quite easily. And that's because carbon fiber is stiff. So if you get it to flex at all, it's going to crack, especially when it's only one layer. Kevlar I found to be quite durable, but you could still dent it, and it's expensive, and it's hard to cut. Got to have special scissors, and it can be hard to lay up. Kevlar has a tendency to float on some epoxies, and then you add extra epoxy, and then you end up resin rich. There's a variety of challenges to working with Kevlar. However, the fiberglass was a little bit more sensitive to dents than the Kevlar, but not much. Yet it was much easier to work with. So that's what I went with. And cheaper by a lot. And if you're building a prototype aircraft, you go, look, good enough. I don't want to spend more money. Might not last forever. Let's just build it and move forward. So that's what I did. Now that it's been in use, well, I got my fair share of dents in my D-tubes. And they're not structural in any way, but they are unsightly, and they're not good for the aerodynamics. And now you'd have to go back and fill them and sand them out smooth and refinish, which would be a lot of work. So I thought, well, here's a chance to improve the wingtip D-tubes by taking a second look at durability and weight. Quite often a good place to find ideas is in designs that are already out there that are successful. There's not a lot of successful foot-launched flying wings, like 2 of them maybe. Now the Swift and I believe the Millennium also use foam core like I do. In fact, I use foam core because that's what they were using on the Swift. They used Divinycell, 1/32 inch thick and 1/16 inch thick. You can't get Divinycell anymore in those thicknesses, but you can get the RX foam down to 1/16 of an inch, so that's what I use. And it provides a nice bonding surface where you don't have to worry about little delaminations too much. So that stays the same, and I take a look at the Swift for its full sandwich panel design, and it is a tad unusual as far as sandwich panels go. First of all, it's asymmetric. They have 2 layers of this Kevlar on the outside, 2 layers of 1.8 ounce 120 Kevlar on the outside of the sandwich panel, and they have 1 layer of it on the inside. And that's an interesting combination, and it is generally considered not a good idea to make asymmetrical sandwich panels, but in the ultralight aircraft world, sometimes it makes sense for a lot of reasons. Now, it might be the case where they can carry all of their needed loads in the Kevlar on the inside skin only. I don't know for sure how that was designed. But Kevlar is nearly as strong in tension as carbon fiber. I think there's some Kevlars that might actually exceed some carbon fibers in tensile strength. And in compressive strength, not nearly as much. So there's other aspects that you can work the design to get the compressive strength that you need and reserve the Kevlar for just getting the tension loads. So, 2 skins on the outside. Now, recently I had a chance to spend some time with a friend of mine who's got a slightly older Swift that has quite a few hours on it, and I gotta admit it was in much better shape than my wing. My wing's only a year old, and I know he doesn't baby that Swift. He lives a normal life, and it's in really good shape. And I had to attribute that to the 2 layers of Kevlar on the outside. And 2 layers of 1.8 ounce, well, that's not too far off of 1 layer of 3 ounce, right? 1.8, 3.8. Well, that's pretty close. And you have to add as much resin as there is weight of cloth. Well, 3 ounce, 3.8, not a huge difference. So I can get 2 layers of this instead of 1 layer of the fiberglass. Oh, well, yeah. And I noticed that the durability on the Swift seemed to be pretty good. So I made up some sample panels. I got a piece of one here somewhere. Let's see. Let's get out the bigger one. So I made one. Got 2 2 layers of Kevlar on the outside, this cloth right here. And I put my fingernail on this, and I go, wow, it's really dent resistant. It just bounces back. And I'm pressing hard, pressing really hard here. And it's some spots, it sort of leaves a mark. The durability between 1 layer and 2 layers, it's more than just double. It's practically dent-proof. And that's the nature of Kevlar. It's flexible, it gives. That's why they use it in bulletproof vests. It doesn't fracture, it flexes. Well, that's pretty cool. So, for essentially the same weight as fiberglass, I can get an almost dent-proof surface with the 2 layers of Kevlar. Yes, it's expensive, but would you rather have to stop every year and go fill in spots and smooth them out and then recover the whole thing? Or would you rather spend your money up front? So pay me now, pay me later. Okay, so 2 layers of Kevlar. But if I put 1 layer of Kevlar on the inside, now I got 3 layers of 1.8 ounce cloth. And over here I got 3 ounce, and I think this carbon fiber was like 2.5 or 3 ounce on the inside. So I got a total of like, well, we'll just round up, we'll say 6 ounces per square yard. So if I go 1.8, 1.8, 1.8, that's 3, and another 2, 4, 5. Now I'm at my 6 ounces. I'm not any lighter than what I have here. I'm more durable, but I'm not any lighter. Oh, okay. So let's think about a different cloth on the inside. I said, oh, 2 ounce. 2 ounce fiberglass. That's a 30% weight reduction. And well, it's pretty strong. E-glass is pretty strong. Thought through this. And that's what's on the inside here. So I made up a panel. And as you can probably see here, it's 2 ounces per square foot. This D-tube is 2.5 ounces per square foot. So that's a significant weight savings. 20%. Nothing to sneeze at. You can save ounces and ounces and ounces, and they add up to pounds when you're doing the whole aircraft. So maybe this would work. However, as you know, the carbon fiber, I designed this so the carbon fiber is enough to carry all of the loads of the wing, and it's carried on the inside of the panel, and this is just to smooth out the surface on the outside and protect the foam and all that. The fiberglass is not going to be enough to do that job. Fiberglass doesn't have anywhere near the strength of the carbon fiber. So I have to now, instead of just saying that this is decorative on the outside, 2 layers of Kevlar have to carry some load. In fact, 2 layers of Kevlar on the outside here is enough to carry all the loads. I don't need any inside skin at all in terms of carrying the bending and torsional loads. And I sort of made up a sample here. This has got 2 layers of the 2 ounce fiberglass on it to kind of simulate, rather than using up my expensive Kevlar, simulate what would happen. And you can have D-tube material that was foam on the inside and some type of composite on the inside and wrap it around ribs and all that. But this definitely is not going to have the durability that you need for regular operations. So I have a material on the outside that will carry all the loads, and I have a material on the inside that is not quite strong enough, but the whole structure is lighter than what I currently have. In fact, the weight savings for the whole wing, somewhere around a half a pound. And if I can save a half a pound in this aircraft, I'm down with that. I'll do that. Because you save a half pound here and a half a pound there, and pretty soon I got a couple of pounds I don't have to pick up and run with anymore, which is good by me. So I have to get the loads from the inside skin to the outside skin efficiently and effectively. Will the foam do that? Maybe, maybe not. I don't know. I don't even know how to test it accurately. I made some tests in the past where I've bonded onto this side and bonded onto this side and pulled on a thin strip of it. But because you're working with a thin strip instead of a large panel like this, small variations in the bonding give you scattered results at best. So I haven't got good answers that way. We know that the foam can't carry a lot of shear strength, doesn't have a lot of shear strength, can't carry a lot of load because it's styrofoam essentially. So why don't we try to not solve that problem in terms of determining how much shear load can the foam take? Those shear loads are spread over the entire foam surface, top and bottom. But let's ignore that for the moment and say, what material would transfer the loads between inside and outside? Well, on many D-tubes, they just bring these 2 skins together. They taper the foam and bring them together, and then you do transfer the loads directly. spar to skin. And the skin then gets split apart, goes around the foam, and comes back together on the bottom. Wonderful way to do it. Really difficult to build at home that way. To build accurate enough so that you have that taper just right on the foam, and everything lines up just right so that that butts right to the spar, so that you don't have any stress risers. It's not something that you can count on the average home builder getting correct. Factory built in molds, yes, but not for a home builder. So I'm going to have something that's for a home builder. And then I thought, nature made the first and most wonderful composite material ever called wood. Wood is a fabulous material. It's incredible strength to weight ratio, carries a lot of shear load, inexpensive, half the cost of our modern composite materials. I can go out and buy spruce for a fourth the cost of a strip of carbon fiber stuff. And it's easy to glue to, it's easy to cut, it's easy to sand, shape, all that other stuff. Wood is an amazing material. And not to be sneezed at, balsa wood and basswood. You might think they're just for model airplanes, but that is not the case. They've been used in full-size aircraft for 100 years. So, basswood, balsa wood. I could do what I did on the trailing edge of the wing, and I can put in a strip of basswood in here that's fairly wide. Now, these D-tubes are made oversized, right? Because it's a cut-to-fit process. It's not build to size. It's fit and cut until it fits. And then that's the size you end up with. So this is extra large from here to here, and there's a trim distance here so you can fit the part. If I made the wood strip wide enough here, well, no matter where it ends up, there's going to be wood there, and just cut it off. And it provided the woods, at least a half-inch wide or so, I'll be able to carry plenty of shear loads, and I'll just transfer the loads through the wood. Hard balsa would probably do the trick. 20, 22 pounds per cubic foot. It'll probably work out pretty good. So that's what I'm going to do when I make the new D-tubes. In fact, I'm probably just going to run hard balsa in here. It's easy to get. You get 4-foot long strips of it, and cut through it with a box knife, and a straight edge, and fit it to the wing that way. So I'll bond the fiberglass to the spar. Fiberglass is bonded to the hard balsa, and the hard balsa is bonded to the Kevlar. And we get all the loads transferred that way. And when it gets all glued together on the wing, I might just wipe a little bit of epoxy down there to protect the wood from exposure. Not that the wing would ever sit out in the rain. We wouldn't let that happen. Would we? So there's the answer right there. 2 layers of Kevlar, fiberglass. Okay, great. So we're almost done, right? No, I got other samples to show you here. Let's look at this one. Let me do a little aside and show you this piece here. This is a piece of the wing skin from the root area of my wing that's after the spar. And this is one layer of 3-ounce fiberglass on the outside and this Technor scrim cloth on the inside. And these are really lightweight panels. But here's the problem. I can take my thumbnail and run it on here and literally cut right through the fiberglass with my thumbnail. Look at that. That's not durable enough. That doesn't cut the mustard. And that's where Kevlar would be much better. However, Kevlar has a drawback. If you've ever sanded Kevlar and nearly lost your sanity, I know why. When you sand Kevlar, because it is flexible, not stiff, when the fibers come up during the sanding process, they don't snap off like fiberglass. Fiberglass is glass. So when the fibers begin to be exposed by the sanding, they just snap off, pop, 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 and you have a fairly smooth surface when you're done. Kevlar, on the other hand, just bends over and just shreds out and gets frayed and all that, and you end up with this really fuzzy surface. Now, I know you can't see the fuzziness here, but it's here, and it never goes away. You can put filler on this and try to sand very carefully, wet sand and all that, and it'll still be fuzzy. You put paint on it, sand the paint. That fuzz will never go away. You can't get rid of it unless you put a thick layer of epoxy over it and don't even sand all the way through the epoxy. But that's heavy. So there's an issue with repairability. we'd like to be able to repair our wings rather than having to replace an entire wingtip panel at $1,000 or $1,500. We don't want to do that. We want to be able to fix it. We want to be able to cut a section out, drop in a new sandwich panel, put a patch over the top like this, and I'll put a link in the description of this actual repair process because I demonstrate it. And you bond that on the outside, and then you sand the edges down, taper them down, and put in some filler, sand that, paint over the top, or any other type of covering that you're using. It works out great. I've done some amazing patches that way. That's not going to work with Kevlar because of these fuzzies. And the fuzzies can drive you insane. So I had to find a way around that. How can I do that? Put on an extra thick layer of epoxy when you mold it. Yeah, that's one way of doing it. But that's a bunch of weight that's not doing anything for you other than just you're carrying that weight all the time in case you happen to break that part so you can repair it later. That's kind of dumb. I'm not going to do that. That's just dumb. So I got fiberglass on the inside, 2 layers of Kevlar on the outside. Well, we'll just think outside the box a little. What surfaces are sandable that are good composite materials? Oh yeah, fiberglass. Fiberglass sands really nice. But I have Kevlar on the outside. Well, does it have to be on the outside? No, really. There's only a 16th of an inch difference here, inside, outside. Doesn't make too much difference. So I made up another panel. I says, what if? Let's put 1 layer of Kevlar on the inside, 1 layer of Kevlar on the outside, and then a layer of the 2-ounce fiberglass over the top of that. And that gives me about 3/1000ths of an inch that I can sand before I hit Kevlar in case I need to make a repair. So now I have a repairable composite panel, and I have all the layers of cloth that I need for my strength to weight ratio. It'll still be lightweight, still strong enough. And now the last question is it durable enough? 1 layer of fiberglass, 1 layer of Kevlar, any better than just 1 layer of Kevlar? Well, here's 1 layer of Kevlar here on the back side. I've made a couple marks already. I'll do another one here. And I run my thumbnail on this. Now, of course, it doesn't go through like the fiberglass, but if I give this enough angles, you'll see where I've made a dent here in it, like that. So 1 layer of Kevlar is not enough. 2 layers is pretty much bulletproof. The marks are not really permanent. They bounce back. So fiberglass and Kevlar. Let's try it again. Let's push hard. Wow. Almost as good as the 2 layers of Kevlar. Not quite. So you can press it hard enough and leave a little bit of a mark there. If you had a sharp stone or something, it's going to make a dent. But it's not going to penetrate through it. Kind of bulletproof. Kevlar bulletproof. So same materials, just resequenced. Sandable surface so it's repairable. Kevlar for durability and strength. Kevlar for strength on the inside. Same weight panel. Oh, there's a good solution. Meandered my way to a workable option to make new D-tubes that are lighter weight and more durable. And that should enlighten everybody as to why it's important to do trade studies and to think outside the box and just try different things and find out what works out. And be willing to compromise on previous requirements like really low cost and say, oh, okay, that was an interesting trade to start with, but it really didn't work out that well, so I've got to do something different. And don't be able to, and don't be afraid to try different things. So I have my answer, and I share that answer with you, and I hope you can use it on projects going forward. And I'd like to close out here by talking a little bit about trade studies, a little bit more about them, because I get comments on a regular basis from a wide variety of people and say, why did you do that way when you know that, well, I give you an example. One guy says, how come your cap strips are on the side of your spar near the top, but not at the top? If you put them at the very top, it'd be stronger. I said, yes, you're correct. It would be stronger. And I said, but if you sit and do the calculations, you'll find out that that difference is minimal at best. And he actually did come back to me. I think he came back and says, oh yeah, I checked and you're right, it's not much difference. I said, at most, it's somewhere between 1% and 3%. Well, 1 or 3% is next to nothing We carry 10% margin on a regular basis on designs like this. So, not a big deal. So why do you make choices like, oh, I'm going to carry my loads on the inside, or I'm going to make this panel asymmetrical, or I'm going to put my stronger material on the inside or weaker material on the outside, and all this stuff that seems non-optimal in terms of structural design? What's for other reasons? It's to make it easier to build, or easy to repair, or cost-effective. So when you design an aircraft, there's a myriad of requirements that must be addressed. Otherwise, you'll end up with what we call a point design. It's good at doing one thing. It's aerodynamically perfect, structurally unsound, weighs a ton, can't pick it up and run with it, but aerodynamically, boy, it's gangbusters. But you see, in aircraft design, you can't do that. You have to balance your requirements, is what we call it in the industry. And we use a structured methodology for that in systems engineering, where we establish parent requirements and child requirements and a hierarchy of those requirements. And you can do something very simple at home that goes the same way. You can say, here's what my design must absolutely do for me. This is what I want to achieve. And you put those at the top of the list. And then you write down every single requirement that you can think of that needs to be met in terms of completing that aircraft design, in aerodynamics, in structure, in propulsion, in durability, maintainability, repairability, buildability, all of it. You know, put them all down and say, and you start ranking them. Go, this is more important than that. That one's more important to that. You get them on your list, and you track them, and you make sure that you're meeting those requirements as you go along. And that is a classic system engineering process, and that's how you end up with designs that are better optimized. Good engineers can just do it in their head, but I highly recommend that if you're working on a design, you write them all down. And if you're a budding designer, you're just getting into engineering, keep in mind that what you're taught in one classroom and another classroom and another classroom all have to be blended together eventually. And that means sometimes this one over here that you've been taught, this is the best way to do it. You have to fudge on that a little bit, and allow a little bit of give, because you got to meet another requirement over here. And that separates the men from the boys when it comes down to designing an aircraft, is how you balance out those requirements. And the really superior aircraft designs are just a better balancing of all of those requirements. So when you see my presentations of a lot of this stuff, and you begin to think, well, that's not the optimum way of doing that. Well, I've done it that way probably because of some other requirement I'm trying to meet. I'm trying to balance out all those requirements. And that's how that works. So I hope you've enjoyed this today. I hope I've been able to impart some knowledge and bring you up to date. This Saturday, 2 days from now, we're going to go out and try to test the extended elevons and some different elevon shapes. We got 1 day of really good wind on Saturday. My buddy Dave has offered to help out, so that's fabulous. And provided Mother Nature doesn't thwart me again, we will know by the end of the weekend, hopefully, whether or not I really do need to build these new outer wing panels and extend the elevons. So until then, as always, I tell you, fly safe and bye for now.